we've got a thin plate with constant density, and it covers this region here. This question asks us to calculate the so-called polar moment of inertia about the origin. Now, we talked about this in the previous lecture, but here we'll use polar coordinates. And this is, in general, a good starting point for calculating these polar moments of inertia. And I'll show you why in a minute. Okay, so let's draw our region. Okay, it's the unit sort of a disk, but just in the first quadrant. So let's call that R. So that's where our plate is located. The polar moment, so let's just put this into polars. So here, R is just our region R. If I wanted to draw something in there like that. Little r is between 0 and pi on 2. Oh, sorry, that's theta. Theta is between 0 and pi on 2, and r is between 0 and 1. Now, polar moment of inertia about the origin. It's just okay, so it's just going to be this. Times delta. So you've got some density. Yes, the density function's in there as well. So this is delta times x squared plus y squared. Okay, now in here delta's a constant, so it's equal to 1. So we're not going to worry about that anyway. Let's put this into our polar form. So delta's just 1. Theta's between 0 and pi on 2. R's between 1 and 0. Now, replace x with r cosine theta, y with r sine theta. And replace dA with r dr d theta. Now, hopefully you can see how the change of coordinates is going to really simplify that. Okay, the x squared plus y squared is pretty much going to simplify massively, and I'm just left with a reasonable integration. So cos squared plus sine squared equals 1. So I'll get r cubed dr d theta. So I want to do the inside integral first. I'm going to get a quarter, and then my final answer should be pi on 8. Okay? Now, if you didn't move to polar coordinates, think about how you would describe your region in Cartesians. You'd have to get the equation for this sort of upper bounding curve. You can get it, it'd be something like y equals positive root squared. And then you'd have to integrate, put that nasty square root sign into your integral and integrate it again. So that's one of the motivations for these new coordinates, these new substitutions. You don't want to be messing around with nasty square root signs in your, or any other nasty things in your integral signs. Okay? I mean, if you want to, you can try to do that without using polar coordinates. Be my guest. Be my guest. But you want to make things easy, not hard. You want to work smarter, not harder.